for being almost all of you on time. Perfect. And okay, we go for the second lectures of Antoine. Again, like this morning, don't hesitate to enter the speakers and so on.
Yeah, yes, please do ask questions during the lectures.
It's easier for the timing that you ask questions during the talk than at the end.
Especially because I know that usually I'm pretty fast, so if you want to slow me down, the only way is to ask questions, right? So all right, so this second lecture is going to be much more experimental than this morning, and is going to be devoted now really much more to a given platform. And this morning we're kind of general, trying to introduce what is an interaction between atoms, so hopefully now you know, you have kind of understood where the van der Waals interaction comes. You have also understood that you have a second order interaction, which is the van der Waals, or a resonant dipole-dipole interaction when you have two degenerate states, so EG and GE. I'll come back to that today. So now what we're going to do is to look at that from a more experimental point of view. So we're going to look at how you can create arrays of atoms in order to explore this physics. I will give you a basics of Rydberg physics, so kind of the essential properties that you need to know in order to understand the many-body physics we're really going to do tomorrow. And then I will gradually move towards the many-body physics by exploring just the case of two atoms. So essentially, I will illustrate what we've done theoretically this morning on examples with atoms for which you can vary the distance. Okay? So I think that now that I'm going to, so essentially the platform we're going to discuss is this one, right? So this is a single shot image of atoms. So each of these dots here corresponds to an atom. You're going to see how we generate that. Each are separated from its neighbor by a few micrometers, so you can essentially address them. And at this distance, they do not interact if they are in the ground state. I mean, that was one of the problems that I asked you that you can look. So if the atoms are in the ground state, the van der Waals interaction in terms of frequency is on the order of 0.01 Hertz. So it's an extremely tiny energy, right? So it's almost unmeasurable. So at this distance, essentially, the atoms do not interact. Okay? So if you want to make them interact, you need to enhance this interaction, and this is what exciting them to Rydberg state provides. So this is the two ingredients that we combine in this platform, large spacing arrays and Rydberg interactions in order to make them interact in different. Okay? So as most of what I'm going to discuss starting from now is done in our group, and once again, I do insist on the fact that everything I discuss is independent of the platform for most of it. So it's just a way for me to illustrate some concept about many-body physics, of course with a bit of details on the Rydbergs, but still, so now I need to acknowledge the fact that all this work is done by a team of people, obviously, so at the Institut d'Optique, so I'm not going to describe all of them. I just want to point out that tonight you have this guy here, Antoine, who is sitting somewhere here, will give a poster and something which is very much related to what Darek discussed this morning that we try to explore experimentally. So if you wish to discuss with him, please do that. And I also, I mean, it's a bit early for you to look for postdocs, but in case you know of anyone who would like to do a PhD, please, we need to have to hire people this year. All right, so enough for the advertisement. So now this is the outline of today. So first, how do you create these arrays of atoms? That will be the first part. Then a bit of Rydbergology, so the scaling laws, the strength of the interaction, and then we will dive into how you measure the interactions between two atoms. All right, so let's start with some experimental considerations. So the first thing you want to have is an array of atoms. So those atoms, they do not, well, you need to trap them. They're in free flight, otherwise they move. And so the way we trap them is by optical trapping. Okay, so we need briefly to recall or to recap a bit how you trap atoms using optical traps. And it's always a good idea to have two different ways to explain that. One which is purely classical because you can have it, and another one which is quantum. Okay, so let's start with the classical one. You all know the argument. You shine a laser on an atom, and an atom is a polarizable object. So the field of the electromagnetic field, which is the light here, is going to induce a dipole. This dipole is essentially proportional to the electric field you apply. Okay? And so now this electric field and the dipole that it has induced will interact with each other, and will lead to an interaction potential. So essentially what you have is an interaction energy which is on the order of minus d dot E, where d is itself induced by the dipole. So this is something which is minus alpha E squared. So if I want to calculate kind of the average energy, average means as a function of the fast oscillation of the light, which has a frequency omega, then this is an energy which essentially is proportional to the intensity of the light. Okay? But of course, it doesn't work in all regimes. It works if alpha is a real number. And you may remember from some model that you studied when you were younger, which is this model of the classically, this model where the electron is elastically bound, yes, to the nucleus with a frequency omega naught. You may remember that the frequency, the polarizability, has this shape. It's a Lorentzian it's a dispersive shape, okay? And in particular, in the tail, this falls down like 1 over omega naught minus omega, okay? So this is kind of important because you remember that there is another component, if you are very close to resonance, that you need to consider. This is the dissipative component that now has a Lorentzian shape. So that would be the imaginary part, if you wish, of the polarizability. It has a Lorentzian shape, which is to say that in the wing, around the frequency, it's case like 1 over omega minus omega naught. So it's very important to use this argument to be sitting away from the resonance, not too far because essentially the force becomes negligible, or the potential becomes negligible, but somewhere here where you've killed the dissipative part of the force, which quantum mechanically would be a spontaneous emission, if you wish, but you still have a non-negligible effect of the light on the atoms in the way of this dispersive force. This is clear for everyone, this? Okay, so we do not sit on resonance, we sit slightly outside in order to avoid this. And then the interactions between the atom and the light is conservative. Okay? Well, this is the first argument. So now what we need to do if we want to have a potential, we need to shape the light field so that the intensity varies in space. Okay, so that's what we need to do. The second type of argument now is completely quantum. Just take a two-level system, shine light on this two-level system, detune from the red, for example, in this case, with respect to the transition. You may remember that then those two energy states are shifted by the AC Stark shift, which is essentially is the square of the Rabi frequency divided by the detuning. The detuning is this quantity, omega naught minus omega. Okay, you remember that? Most of you, you've seen this. So the Rabi frequency is connected to the dipole matrix element here through h bar omega is d times E. Okay, and once again, d is the d we've introduced this morning, which is the matrix element coupling E and G. All right, so now what this means is that if the intensity is the highest for omega naught larger than omega, then the energy is the smallest, and essentially it means that the atom is a high intensity seeker. It's going to look for the place where the intensity is the highest. Okay? Same argument now, if you make, so omega squared, this is the same as E squared essentially, which is intensity. So you need to shape the intensity in such a way that there is a maximum of intensity at the place you want to trap the atoms. Of course, the only drawback of all this is that if you look now at the real numbers and you try to estimate what is the depth of the potential you can create, which is to say the action of this dispersive force, it's very weak. It's so weak that actually the kind of trap depth you can create is typically in the 100 of microkelvins or 1 millikelvin. So if you want to use on atoms this dipole force, as it is named, you need to start from a sample which has been laser cooled before. Okay? All right. So now, as I said, we need to shape E squared so that we have a place where the atoms are going to be attracted because this is the place where the intensity is the highest. So there are essentially two ways of doing that. The first one is to create what is called an optical lattice. So essentially you take two laser beams, like this one and this one in opposite direction, and you create a standing wave. Okay, so in standing wave, you've got places where the intensity is low, it's high. It means that in the place of high intensity, you will be able to have a minimum of energy of the atoms where they're going to be located. They have a tendency to be attracted there. You can, of course, do that in one dimension, in which case you've got some kind of pancakes of trapping potential. Or you can go in two dimension by interfering two orthogonal standing wave. And in this case, the trapping potential will look like arrays of tubes. Okay, everyone sees the geometry. It's always a bit... Or you can do it in three dimensions just by intersecting three of these laser beams, standing wave. And in this case, you create a 3D lattice. And essentially, by varying the geometry of the angle of these three axes here, you can kind of shape and tune the spacing of the atoms in the array. But typically, the spacing is on the order of the wavelength of the light, because this is the interference of two light fields. Okay? So I'm not going to give you too many details, but this is, of course, a very, very important platform in cold atom physics, and people are using that a lot. And there was, over the last, let's say, 8 years, a very important development is that people have combined this optical lattice with what is called a quantum gas microscope. So essentially, this is a set of lenses with a very large numerical aperture. So in this way, the diffraction limit of these objectives here is such that you can resolve spots that are located at a typical distance, which is on the order of the wavelength. So there were several groups who started that, essentially two of them, Emmanuel Bloch and Markus Greiner, and they kind of got the result at the same time, and now there are many, many groups who have this platform, but essentially, I don't know if you can see here, actually, how do you lower this? No, ça marche pas. You can see the spots, so essentially the fluorescence here, this is fluorescence image of atoms that are trapped in a 2D structure, and each of those spots corresponds to one atom. So indeed, you can resolve the atoms in these arrays. It's a bit of a reconstructed image, but it doesn't matter. Okay, so this is the first platform, a very popular platform. And over the last 10 years, a new platforms kind of appear, which is based on what is called optical tweezers. So optical tweezers are very popular among biophysicists. Actually, they've started this thing. But it's using the dipole force in order to trap with a single laser beam one atom. Why can you do that with just a single laser beam? And you do not need to resort to the interference I was describing before. Well, I mean, if you think of a laser which is focused by a lens, at the focal point, if I zoom, I actually have a Gaussian beam. And the Gaussian beam is focused on a size, which is typically what is called the waist. This waist is set by the numerical aperture of the lens, lambda over NA, with some numerical factor, but it's not too important here. And importantly, in the last direction, it's set by what is called the Rayleigh distance, which is the waist square over lambda. So it means now, if you focus the light on a size which is on the order of the wavelength, so you use a numerical aperture close to 1, then the waist and the Rayleigh distance are in the same order, and it ensures a trapping in 3 dimensions with just a single laser, without having to resort to interferences. Okay? Right, so indeed here what you do, you take a laser beam, focus it in the center of the chamber, and in this plane here you create this trapping potential, which has this shape, essentially the shape, the intensity profile of the light along this axis. Is this clear for everyone, this? All right. So now you want to fill this thing, so how do you do that? Well, I told you that you need to start from a cloud of cooled atoms. And so we start from what is called magneto-optical trap, doesn't matter, but essentially this is an ensemble of atoms that have been pre-cooled by laser cooling down to a temperature of about 100 microkelvin. And this cloud acts as a reservoir for the tweezer. So the atoms are going to enter at random in this very small volume. The problem is that I told you that the potential is conservative because we put the light away from the resonance. So in principle, if an atom enters, it should be able to exit. So why does it stay in the trap? Because at the same time, we've got 2 laser beams that ensures the cooling to produce the reservoir. And this cooling applies a friction force on the atom. It's a radiation pressure force. So those lights are now almost resonant with the frequency of the atom, while this one is different, omega is different from omega naught by a lot, so that you are in the way. So you see, you use 2 types of force, the radiation pressure force to cool the atoms, and the dipole force to trap them. So now the atoms enters, and it's kind of trapped here. Its motion is damped when it enters, and it stays in this region. It stays in this region, and at the same time, because it sees this light, it scatters photons. So it fluoresces. So this fluorescence you can collect onto a camera. And essentially the light from here is collected onto 1 pixel of the camera. And you can look as a function of time, for example, what is the signal that you get on this thing. And this is a typical example of a fluorescent signal. Typically is the number of photons you collect as a function of time in seconds. So essentially it means that you start from a background, and at some point one atom enters in the trap. It tells you, hey, I'm here, you can start the experiment. You keep it for several seconds, up to 20 seconds typically. And then at some point, then you lose the atoms. The striking feature is that you never have double steps, which is to say that you either have 0 atom or 1, but almost never 2 at the same time. Why is that so? Because it turns out that when you lose the atom, what happens is that a second one has tried to enter in the trap. And for a very short amount of time, you've got the 2 atoms at the same time, but it forms a molecule which decays with a lot of energy. Okay, so essentially you cannot trap these molecules. It releases a lot of energy, and as a consequence, it's either 0 or 1 or 2 for a very short time before you lose the 2 atoms. So in practice, it's 0 or 1. Okay, so this creates a single photon source. It's non-deterministic because you have no idea when the atoms are going to enter. But at least as soon as the atom is here, you can start the experiment. So it's a heralded in the sense that it's annoncé, as we say in French. So you can put a threshold here, and you decide whether you've got 0 atom or 1 atom. All right, so which atoms have been handled this way? Well, now many, actually. Until 2 years ago, it was not the case. It was only rubidium, essentially. And so this is the periodic table where all the elements, I hope I haven't forgotten any, that have been laser cooled. So it starts to be a fair amount now from the first period, the first column of the periodic table. Essentially, a lot of rare gases have also been laser cooled. Now you've got a lot of activities on this second column plus this lanthanide stuff. And so the ones that are in red are now the ones that have been trapped in tweezers using these things. So you see that there is now a fair amount of atomic species that are trapped using the technique I've just described. So now you want to create a many-body system. So you want to have many of these atoms, obviously. So how do you do that? Well, you use diffraction. Before sending the light onto this large numerical aperture lens which creates a dipole trap, you place a diffraction pattern. It's a spatial light modulator which is based on a liquid crystal, a bit like the kind of thing you've got in these video projectors. So what this does is that it imprints a phase on the wavefront. Okay? And you probably remember from your early days of diffraction, when you studied optics at university, that if you place here some kind of phase factor, what you have in the focal plane of the lens is the Fourier transform of the phase factor. So in intensity, this is the modulus square. So now it turns out that if you want to have a given, so essentially what you have spots, which correspond to the diffraction order. So you can revert the problem and calculate the phase you need to imprint on the light in order to have a given geometry of the arrays in this thing. So this is an example of a real phase pattern, as we said, so coded over 0 and 2 pi, using this spatial light modulator. And this is the resulting pattern that you've got in the focal plane. So those are the laser beams that can be arranged in here. It's in kind of a Kagome type of lattice. Those are not atoms, and those are laser beams that you measure after the chamber. So as far as the atom is concerned, now we have a problem, obviously, which is the non-deterministic nature of the loading. So this is a real-time movie where you see atoms entering and leaving in a 10 by 10 array. So all the small square that you may see here corresponds to the regions where the atoms are supposed to be trapped. And you see that it blinks. The blinking means an atom enters and leaves. Okay, so that's kind of obvious. You never have all the traps filled at the same time. So this is kind of a problem for this thing. But now the solution is that if I want to have a given array, let's say out of the 10 by 10, I can subdivide a small array, and I want to fill all the atoms of this subarray. So what is the solution to that? Well, it's reasonably simple. You move the atoms, so you take this one, you put it here, you take this one, you put it here, and so on and so forth. How do you do that? Well, you use an extra laser beam. And this laser beam is like a moving head, exactly the kind of thing you would have, for example, in a CD player. Okay? This is a laser, tightly focused, that you can move. And you grab the atom. So essentially, an atom is placed at this location. You grab it with the tweezer, so you increase the strength or the amplitude of the moving tweezer, moving by 10 micrometers, and drop it gently at the position where you want to put it, in the target position. So the thing which is amazing with this is that it works. Because at the end of the day, you move atoms one by one. And it works extremely well, with more than 99% probability. And so that allows you to really build structure with a non-negligible number of atoms that are completely on demand. So all these pictures now are again fluorescence image, but single-shot fluorescence image. You start with this initial random configuration in a 10 by 10 array, and after you move some of the atoms, you can arrange them in line, circle, square, a more complicated structure. Okay? So this is deterministic. You take an image and you see where the atoms are. So essentially the procedure is the following. You start with this kind of array, measure where the atoms are, compute how you need to move them, move the atoms one by one, and check that you have indeed the configuration you want. So now we can arrange up to more than 200 atoms. So it's actually a fairly large number, and much larger than what people do in optical lattices, actually, for certain examples. We can do that in totally random patterns. So who can guess what this thing is? Yes. So this is this. Okay. A pale version of it, I agree, and probably doesn't sell the same amount. But okay. We can also do other more interesting things. If you look at this structure here, this is an hexagonal structure, which is the one that you find in graphene, for example. This kind of structure here is called the Kagome lattice, and this is the kind of structure that is relevant for the study of magnetism in some kind of compounds called Herberti-Smith, which exhibit geometrical frustration. It doesn't really matter, but essentially it means that we can create structures that are relevant for condensed matter physics. All right, so this is something we, yeah?
For how long this kind of structure can remain in time?
At this structure, it remains for, okay, in a single trap for about 20 seconds. Okay. But the time it takes for, if you want to keep the full structure, obviously it's 20 divided by the number of traps. Okay, so typically it's a few hundred milliseconds. But all the experiments we'll do in a sub-microsecond time scale, so essentially it's the age of the universe. All right, so I mean, so we were the first kind of doing this kind of thing, so now there are a lot of groups that do that, so I'm not even daring any longer to cite them, there are just too many of them. But the thing which is very nice is that it also works in 3 dimensions. So this is an example, sorry, yeah?
I was wondering how much time it takes to move the atom?
About 1 millisecond per atom. So essentially in about 100 milliseconds, you move 100 atoms. Yep.
And what is the expected lifetime of the atom inside
About 20 seconds. Yeah. And it's only limited by the vacuum, so if you improve the vacuum, you can keep them for longer. Yep, you have a question?
Yeah, I just wanted to ask maybe the same question for 3D case.
Yes.
Does it take much longer, or is it...
It takes much longer because we do the sorting plane by plane. So essentially, your 3D structure is an ensemble of planes. And what we did up to now, but I mean, there are ways to go around that. But so you need to indeed do the sorting plane by plane. So you multiply the number of planes, so it's very time consuming. At the moment, we don't have a good way to do it.
I guess the experiments which are run on these structures afterwards, they need to be repeated a lot of times?
I'm sorry, I didn't get it.
The experiments which are run on the simulation phases, which are run on the structures afterwards, they need to be repeated a lot of times?
Yes, then I will show you that. Yes, about 100 times typically. The duty cycle of the experiment is about 2 to 5 hertz. So essentially, you've got a new configuration every 250 or 200 milliseconds. So you can, repeating about 100 times is a few, half a minute or something like that. So. All right, so the 3D you can do, okay, I'm not going to comment too much on that. You do this useless Eiffel Tower, but it's kind of cute. And you can also assemble in 3D. Okay. Right, so now let's move to making the atoms interact in this structure. By making them Rydbergs. So this is Rydberg states were actually introduced a long time ago. 1889 is the date where Mr. Rydberg, Danish physicist, introduced the Rydberg states, that is to say, highly excited state. In the notes that I will put, so those slides will be on the website, obviously. You will have some references for those of you who are interested in this. So for most of the discussion, and it was true actually until the end of last year, essentially, I will stick to alkalis, just because they are easy to think of. It's just an electron away from a nucleus, which is screened by the inner core electrons. Right? Now people are looking more and more to higher states, so things are a bit more complicated from the point of view of the atomic structure, but essentially the gross physics is kind of the same. Okay, so let's look at a particular alkali atom, which is rubidium. It could be any other one, but this is a popular atom. So this is what is called the Grothendieck diagram. So this is the energy level, and here this is the principal quantum number. So the angular quantum number, and here the principal quantum number. So of course you've got many states. And the Rydberg state, I wouldn't know how to define them, but typically when n becomes much larger than 1, whatever that means, they are called Rydberg. So there is no real boundary between the two of them. And so something which is kind of interesting with those states is that essentially they follow the formula you know for the hydrogen atom. And you all remember your AMO physics class, where essentially if you just take an hydrogen atom, the energy is given by minus 13.6 eV over n squared. Okay, this is essentially the same formula for an alkali. It just turns out that here you need to put what is called a quantum defect. So it's an effective principal number. The reason for that is that if you just look at a real atom, so this is essentially a charge ZQ, you've got the electron, the Zen minus 1 electron, and you've got the outer electron. Okay, so now if L is larger essentially than 3, you find out that the trajectory avoids the core, the electronic core. Therefore, essentially this inner electronic core completely shields the nucleus. So it's completely equivalent to a plus Q with a minus Q around. If L is between 0 to 2 typically, it means that you allow some trajectories to enter the core. And therefore, the screening by the inner electron is not perfect. So it makes the electron a bit more tightly bound, and therefore what you need to do is to change this n by n minus delta L, which is a quantity which depends on the atoms. Can give you a few numbers if you wish, but typically they will depend on L, and typically they're on the order of 3 to 1, depending on the L values. Okay? So I mean, it's kind of a detail of the Rydberg. It's not too important, but you need to know that this is not exactly an hydrogen atom. So now, the more important properties of the Rydberg now comes. And the most important properties is the fact that the size of this orbit, if you want to speak classically, is on the order of the square of the principal quantum number. And if you want to remember why this is the case, there is a model that I guess you've all seen, and which is actually kind of not too much true for the low-lying state, but very true for the high-lying state, and this is the Bohr model. So I'll just remind you very briefly what this states. It's a classical model where you look at the atom as a plus Q minus Q, like a kind of small solar system. You just write that the kinetic or the centrifugal force is equal to the Coulomb force, E squared over R squared. And you impose a quantization rule, which was proposed by Bohr initially, which is to say that the angular momentum is quantized in unit of h bar, where n is a principal quantum number. So now, of course, you can remove the v, and you will find that r is on the order of n squared, h bar square, the mass divided by the charge of the electron. Okay, so you see that without doing too much fancy quantum mechanics, essentially you can recover this formula, which turns out to be exact within a factor 3/2. Okay? So it's not so bad as an argument to get scaling laws. So the consequence of this large atom are twofold. The first one is that the atoms have a long lifetime. I'm not going to do the scaling, but this lifetime would scale like the cube of the principal quantum number. So essentially it means that because the orbit is so large, the radiation of energy is much less efficient because it has a large radius. Okay? The number that maybe you should remember is that typically for the principal quantum number used in the experiment, n is the lifetime is larger than about 100 microseconds. If you were sitting here, for example, the lifetime would be 26 nanoseconds. So you see that this is an improvement by a lot, by about a factor 10,000 with respect to the lifetime for a low-lying state. So this becomes much longer, and that's what allows you to do coherent manipulation. I will talk about that more tomorrow. The second very important properties that we kind of already inferred this morning is the fact that they have large dipole moment. dipole moment means matrix elements of the dipole operator. So it means that this NLM matrix element that I wrote this morning, so this DN Ln prime L prime, which was NLM Dn prime L prime N prime, scales essentially like the square of the principal quantum number again. Okay, and so this is what will lead to this giant interaction that you have for Rydberg atoms. So it has two consequences. The first one is because they have this large dipole moment, they will feature very strong interaction. So this is very nice. Something which is nice and not nice is the fact that then, because they are such a large dipoles, they will couple very easily to electric fields. So that's good in a sense because it means you can use that to control, but it's bad in another way. It is very reminiscent to what Patrice said this morning. Any electromagnetic noise that you have will spoil the coherence of your states. Okay, so you have to be careful when you design your electromagnetic environment not to be spoiled by this. I just want to emphasize this scaling law on this graph. So essentially, this is the radius I just calculated, this Rn square thing, as a function of the principal quantum number. So we operate usually around here. So the size of the orbit is much larger than the size of the COVID-19, which is 125 nanometers. Okay, for n equals 100, you're already at 2 micrometers in size. So you see that here you really are at the scale for the electron trajectories, which is the one of a small microbes, essentially. Yeah? So this is really a gigantic atom, this thing. So it's just kind of a striking number. You can compare the size to biological objects. I mean, the comparison stops here, obviously, but still. Just a few words about history. Rydberg's atoms were introduced in the late 19th centuries, and as soon as people had laser, they started to do precision spectroscopy with that to test some fundamental constants, essentially. And there was a very important work that you probably all know, which was the work done on cavity quantum electrodynamics using Rydberg atoms. So what is it about? Something that people struggled to do a lot in the late 70s, early 90s, was trying to couple one atom with one photon. And in order to do that, the idea, which was applied by several physicists, I mean, the most celebrated ones are Houches, because he got the Nobel Prize for this, but he's not the only one. You take a cavity, and in this cavity, you place an atom, which looks like a two-level system. And so now the interactions between the cavity and the atom is something which is d times E. E is the electric field of the cavity. Typically, this is square root of h bar omega divided by 2 epsilon naught times v, v being the volume of the cavity on the order of the wavelength of a transition. And the thing which is very appealing is this n square dependence, because it makes this interaction atom field extremely efficient, even if this is the field of only one photon. And this is a one photon field. Okay, so you see why it was kind of appealing for this early manipulation of interaction photon atoms, because of these gigantic dipoles. Okay, the idea that interactions between Rydberg could be useful, and especially when combined with cold atoms, came later, early 2000, let's say, by two guys, actually, Pierre Pillet in France and Tom Gallagher in the US. So they were the first one to propose that if the atoms are now frozen in space, the energy scale associated to the temperature is smaller than the one associated to the energy. Therefore, the energy becomes the dominant energy scale, and you can do many-body physics. At the time, it was still kind of, in random ensembles, and a bit hard to completely control. And then there were those two theory papers that kind of robusted the field and also robusted the interest in Rydberg physics. Two proposals by names that I'm sure that many of you know. In quantum technologies, they are everywhere. So Misha Lukin, Peter Zoller, and other people that are less famous but still have a very important contribution. And the idea is to introduce what is called the Rydberg blockade. So let me illustrate this thing on this view graph. Assume that each atom, you've got two atoms, and each of them can be reduced to their extreme simple structure, which is a ground state and a Rydberg state. So essentially, you ignore totally all the other states of the manifolds. And now we're going to consider the interaction energies for this pair of atoms. If the two atoms are in the ground state, essentially they do not interact. That's what we said. Alkali atoms or any atoms in their ground state separated by 10 micrometers, they do not interact. Place one in the Rydberg state, the other one in the ground state, same argument. The interaction is really way too weak. But now when you put the two of them in the Rydberg state, they are in the same Rydberg state, therefore they will exhibit this van der Waals interaction that we derived this morning. This van der Waals interaction scales violently with the principal quantum number, we're going to see, but essentially this is shifted in energy by a quantity which is non-negligible. So now, if you start to drive the system with a laser, the typical bandwidth associated with the excitation is set by the Rabi frequency. So now it means that if you tune your laser on resonance with the excitation of one Rydberg atoms, this is out of resonance with the excitation of the second one. It's not always the case, provided the fact that the atoms are close enough that the Rabi frequency that set the line width is smaller than the interaction energy. So there are two zones, if you wish, the zone above what is called the Rydberg blockade radius or below. But from the point of view of computing and many-body and quantum information, this is very nice, this feature. Because if you do not know which of the two atoms you superimpose, you excite, what you do at the end is you excite a superposition of exciting the first one or the second one. So you've created a state which is 1/√2 the excitation of the first one not having touched the second one, or vice versa. And this is an entangled state. So people had in mind that combining the interactions between two Rydberg atoms in the Rydberg blockade regime, you could build some logics to create entanglements and quantum gates. So that was really the underlying idea of this paper. And when they proposed that in 2000, essentially no one has trapped single atoms yet. And people doing Rydberg physics were totally traumatized about the idea of controlling the interaction. So essentially no one really believed in these things at the time. But still, people tried. First in random ensemble, so I mean the details I'm not going to give you, but essentially you start from a magneto-optical trap. You try to do a Rydberg excitation in there, and because of the blockade, you saturate the number of Rydberg atoms you can put in the system. Essentially, if you've got a random ensemble of atoms, if you've got several atoms inside this Rydberg sphere, this Rydberg blockade sphere, you can only excite one of them. So now it amounts to the number of blockaded spheres you can fit in your huge cloud. So you see that you saturate the number of atoms that you can place in the system. Those were in the early 2005-ish. And so the very first experiment where actually it would work with just two atoms were done actually around 2010, so by our group and a group in the US, where we really saw the first blockade between two atoms at controllable distance. And that was what triggered this field that we're now going to discuss. Any questions so far? Ça va? It's not going too fast? You will not say it to me, at least. You will say it to Quentin later. All right. So, in the last 20 minutes, what I want is to discuss now this idea of Rydberg blockade and to see how we can play with the interactions to go towards the many-body physics. So, I need to do a bit of plumbing first. How do you couple the ground state of a Rydberg, of an atom to a Rydberg state? I mean, for me, it was just called omega in the previous slides, but it didn't give you any flesh about what it is really. What it is really is just a laser excitation. Unfortunately, the transition going from the ground to a Rydberg state, a typical Rydberg state, is in the UV. This is around 300 nanometers for rubidium. It's even more UV for other atoms. So it's a bit impractical from the point of view of lasers. It's hard to get very powerful lasers. They get very easily absorbed by glass, by windows, and so on. But still, so the idea to do this excitation is to use what is called a two-photon excitation. So you go through an intermediate state. I'm sorry, this should be shifted. You are slightly away from the resonance of the intermediate state. And if you do that, piling up two photons, it reduces to a single coupling, which is just the product of the Rabi frequency divided by the detuning. So let me say that again, because this is an argument that we always do in light matter interaction, and Saïda Gelati will actually use this to show you the Raman transition later during this week. But the basic idea, once again, is you've got three states, 1, 2, 3. You couple, but off resonantly. Okay, you've got a Rabi frequency. Let's call it 2, 3, and omega 1, 2. This is detuned by an amount which is delta, and if you adiabatically eliminate this state, which is to say you apply perturbation theory when this population is completely negligible, and it has to be because you are not on resonance. Then you find out that this system is exactly equivalent to a two-level system with only two states, with a coupling now, which is an effective Rabi frequency, which is omega 2,3, omega 1,2, divided by delta. There are factors too, but they are not too important. Okay, so this is something that you will see all the time. So this is essentially perturbation theory, and this is again the coupling square divided by an energy mismatch. You remember this morning we applied that for perturbation theory. We just said this is V square over delta. But this is exactly this formula, which is generalized to the case of three states. Okay, so always the same laws that we apply. So now, of course, if you do an excitation of this system, you can drive a Rabi oscillation. Essentially, it's a coherent excitation. You prepare the atoms in a very well-chosen initial state. You apply the laser, targeted to a well-chosen Rydberg state, so that indeed it reduces to a two-level system. And you measure, after having sent the laser, what is the population of the atoms in the excited state. It's very important to bear in mind that when we do this kind of experiment, we do an experiment on single atoms. And therefore, we need to repeat many, many times, because what you create during the superposition, you remember that mainly from your AMO physics class. The state that you generate when you take a two-level system and drive it with a laser, so there is ground excited, there is omega, let's make it on resonance. This is this omega effective. You will create the state psi of t, which is cosine omega t over 2g, plus or minus, doesn't matter, sine omega t over 2e. Okay, you remember that? So this is the Rabi problem, okay? And so essentially when you do a measurement, once you will find either g or e. I'm not telling you how we do the measurement yet, but I will in a minute. And if you repeat the experiment many, many times, you can measure the probability that the atom is in the excited state, the Rydberg state, which then is sine square omega t over 2. Okay? How do you tell that an atom is in a Rydberg state? So you need to repeat many times. Once again, I insist. How do you tell that the atom is in a Rydberg state? Well, for the simple reason that if you had an atom initially, if you place it in a Rydberg state, it's not trapped any longer by the tweezer. So actually, it moves away. So it's kind of annoying because it's a destructive measurement. You've lost the atoms. So when you do the measurement, if at the end you do not find the atom any longer, it means that you have excited it to the Rydberg state. Okay, so it has some drawbacks, obviously, because if you got any extra losses, it will look like a Rydberg excitation. It's not that. But of course, you can do a calibration. And the kind of fidelity that we can reach is above 96% with this kind of method. Okay? So you can see that actually it's a pretty high fidelity. So we're not talking about the superconducting circuit type of fidelity yet, but we're getting closer year after year. Another thing which is kind of nice is that you can decide to work between two different Rydberg states now. So this one, and you drive a microwave. So the frequency is typically in the 10 gigahertz, and you can drive very long Rabi frequency, Rabi oscillations as well on those two states. Okay? So now what we're going to do in the next 15 or 17 minutes is trying to see how we can measure the interactions between two atoms using all these methods. So we saw this morning that essentially there are two ways for the atoms to interact when we consider only the dipole-dipole transition. There is the van der Waals interaction, which is the second order interaction, which occurs if you look at what happens when you place the two atoms in the same Rydberg state. Then this energy is shifted by the van der Waals interaction. Okay? Or you have the resonant interaction, which is that I can have one atom excited in this S state or the other one in a P state. So here I have two different Rydberg states. We'll come back to that. But so essentially, we'll play with that. So let's start with the van der Waals. So this is the drawing I've already showed you. So essentially, we will look at the excitation of two atoms and assume that the two atoms are very close to each other, which is to say closer than the Rydberg blockade radius. And let's measure what is the oscillation frequency, what is the excitation of the atoms. So what happens in this regime is that essentially this system reduces to a two-level system. Because, I mean, this part of the spectrum cancels out. It's out of resonance. So essentially, I just have this state and this state. But this state is a collective state. This is my state 1 over root 2 Rg plus Gr. So now, the coupling between the ground state, which consists of the 2 atoms in the ground state, or the excited state, which corresponds to only one of the 2 atoms excited, is enhanced by a factor square root of 2. This is what I showed you this morning under the name of superradiance. You remember we had calculated this morning the dipole matrix element connected Gg to D1 plus D2, 1 over root 2 Rg plus Gr. And we said that this was equal to square root of 2 times dEg or drg, the matrix element coupling the two. Okay, so what we expect in this case is that the system behaves completely collectively, 2 atoms in the ground state, or one of the atom excited, this excitation being shared between the 2 atoms, because this is an entangled state. Let's do the measurement. We start with 2 atoms very far from each other, so 2 tweezers separated by typically 15 micrometers, so very far. We measure the probability, after we apply the laser, to excite the 2 atoms at the same time. And what we observe is an oscillation here. You see that this oscillation is not quite an oscillation, actually. So do you know why it looks like this, and what would be the mathematical form of this thing? Remember, the atoms are very far from each other. What's the probability to excite one Rydberg atom? If it's alone, this is this number. So I have 2 of them, and they are independent. So what is the PRR? It's PR squared. That's the probability to excite the first one times the probability to excite the second one. So you have a sign to the 4. So this is the reason why this doesn't quite look like an oscillating, it looks like an oscillating, but not like a sine square. It's actually a sine to the 4th. Now you can go, yes?
There's no decay in the sine to the 4, there is no decay.
There is no decay. So you are worrying about the decay here?
Yes.
Yes, because that's an experiment and not theory. Okay? Yes. And those data are from 2015. I mean, now we can do that with less decay. But okay. No, but it's a good question. Yeah. So now you do the very same experiment, but with the atoms very close to each other. And you measure the probability as a function of time. It's actually omega t that you have here. And you see that essentially it's 0. So when it's 0 and you're an experimentalist, I mean, it's always a bit scary because it can just be that the laser was off when you did the experiment. So it's good to check that on the very same data set, you do have something happening. So we can also plot for the very same data set, so a given distance or this one, the probability that only one of the 2 is excited. Okay? When you have this, well, it looks like this. It varies between 0 and 1/2. I mean, we can calculate the signal. It's not too important. But most importantly, what is important is that when you are in this blockade regime, where on the probability to excite the 2 atoms, nothing happens, and the probability to excite one of the 2 atoms, there is something happening. And not only is there something happening, but it's oscillating faster than here for the same Rabi frequency. How much faster? But precisely the factor square root of 2 that we want to see in this formula for the collective coupling between the 2 atoms. Okay, so this is the signature of the fact that you have prepared when you sit here just this entangled state. Okay, so it's a superposition of those 2 things. But now let's do something a bit different. Let's work away from the blockade regime. In your blockade regime, everything is beautiful because this state drops off. There is only one energy scales that, or time scale that sets the evolution of the system. That's the Rabi frequency. But now I will work on purpose in a regime where omega is on the order of the interaction energy between the 2 atoms. So the dynamics of this system will be set now by 2 parameters, the energy and the Rabi frequency. The Rabi frequency that we can calibrate doing the experiment we just done before. So at the end of the day, this is what it looks like as a function of time to the probability of excitation of 2 atoms at the same time. So it's in between the blockade and the independent case. But let's just do, for the sake of playing with numbers, a calculation on a computer. So this is 3 minutes on any software that you use, or Python or whatever. You just solve the Schrödinger equation for the 3-level system. What are the 3 levels here? Ground, 1 over root 2 Rg plus Gr, and Rydberg. This is an energy E, and this is an energy E plus U, because they interact. So you just solve the Schrödinger equation for this 3-atom system. Once again, the Schrödinger equation, it looks like alpha, beta, gamma dot times I is E is 0, E, 2E plus U, alpha, beta, gamma, in this basis. So this is kind of easy to calculate the evolution of the thing, and what it gives is this curve, which kind of looks pretty much like what we have on the experiment. So you see that now if you know the Rabi frequency, you can extract by a fit what is the interaction energy between the two atoms. And so you can do that, and you plot as a function of the distance, because you vary the distance, you can plot the energy just measured between two atoms. That was the first time it was done, actually, to measure the energy just between two atoms. You isolate them, and you measure the interaction energy directly between the two of them by looking at how the dynamics of the system driven by the laser is affected. And you see the theory, which is the thick line, with some calibrations coming from the experiment, and you see that it's pretty good agreement. So there is no ab initio, I mean, it's an exact diagonalization, and no adjustable parameter in it. So this is not a fit, and this is really the... So you don't learn anything from the physics point of view. You have to be clear about that. We knew what we had to find. Van der Waals interaction is known since a long time, 1930. We know to calculate that from quantum mechanics, so there is no discovery, but it's important to test that indeed we have reached a level of control where you can do the measurement. That's clear? All right, so now we move to the last second type of interaction, which is this resonant dipole-dipole interaction. So what we're going to do now, we're going to work in the Rydberg manifold. So essentially, this is again the level scheme I showed you before, so the ground state, the Rydberg state. But essentially, for what I'm going to discuss now, I'm going to ignore all the low-lying state. I can do that because the lifetime of Rydberg atoms is long enough that I can play with them in the Rydberg state. So I will take a state 60S coupled to a state 60P. The reason for that is then because there is a dipole matrix element connecting the two of them because they have opposite parity. Okay? So, from the point of view of the interaction, what does it look like? Well, it looks exactly what Darek showed you this morning, or what we also discussed. It means that you've got two degenerate configuration. This configuration where you got the atoms in the state P, the other one in S, or vice versa. So you remember that was when this morning I did the energy spectrum. I plotted like GG, EG, GE, and EE. Here you just replace the later. This is SS, PP, SP, PS. Those two states have the same energy, and they are coupled by this d square over r cube. You diagonalize this thing, and it gives you two states, a state plus and a state minus, which are the superposition. So I don't know which one is which, but it's not too important for here. 1 over root 2 RG, which is to say, sorry, SP plus PS, or 1 over root 2 SP minus PS. Okay? So can we measure this process on an experiment? Yes, we can measure this process on an experiment. This is what is shown here. You just take two atoms. Those atoms are separated by 30 micrometers. So this is a very actually large distance. You prepare the first atom in the state S, the second one being in P, and you measure as a function of time what is their state. And of course, again, you need to repeat on many realizations of the experiment, and what you see is a coherent evolution with the two probabilities which are in phase opposition. Okay? What is the frequency of the thing? Well, this is twice the interaction energy. We'll derive it in a minute. Okay? Why is it so? Well, this is the kind of quantum mechanics that you learn pretty early on. Your initial state is what? Let's say it's the state PS or SP, doesn't matter. This is your state at t equals 0. This state I rewrite as a superposition of the two eigenstates, 1 over root 2 plus minus. So now, when the system evolves as a function of time, it evolves toward 1 over root 2 e to the minus vt over h bar, the vt being d squared over r cube, plus minus e to the plus I Vt over h bar. Okay? And so now when you want to calculate the probability that after a given time you are back to the state PS. You just say this is SP psi of t modulus square. And when you do that, what you find is sine square Vt over h bar. Okay, this is exactly the kind of textbook quantum physics that you all learn. Is probably the second practical work that you had to do in quantum physics. So this is exactly that you observe here. Okay. You can check that indeed everything varies well. So you vary the distance between the atoms, between typically 10 micrometers to 50 micrometers. And you do check for the scaling, like the 1/r³ scaling, so it kind of works. And once again, I want to emphasize how surprising this is. I mean, the atoms, I mean, the thickness of a sheet of paper is 100 micrometers. So at half the thickness, the two atoms do interact with a time scale which is 1 microsecond. So it shows how violent the thing is. And this will be useful for tomorrow, but essentially, of course, I mean, someone made a remark this morning when I wrote the DEG square, I forgot the angular part. You remember that? Someone asked this morning. I cannot completely, obviously, and if you just take them into account, you will find that there is an angular dependency of the C3/R3 coefficient. This C3 coefficient turns out to be actually the one you learn from your basic ENM, which is the angular pattern of a dipole, 1 minus 3 cosine square theta, where theta is the angle between the internuclear axis and the quantization axis that set the axis of the dipoles. Okay, and so you can measure for various distance and various angular disposition with respect to a B field, you measure this kind of angular coordinate. So the thick 9 is the theory, and you do find this nice pattern. Okay? Questions? All right, so if there are no questions, I'm done actually. So this is something I've taken from a review paper in 2010, which kind of summarized, even before experiments were done, all the promises of Rydberg physics. At the time, the only thing that had been done were the blockade experiments between two atoms. The people were already jumping towards the quantum information using that. So this is essentially, as a function of the distance, the interaction energy between two atoms. And they were pointing out that actually Rydberg have an interaction energy which is not too far from the one of two ions. Okay, they are close enough. And so now what I've plotted here, this is our version of this plot, but now those are experimental data. Okay, and you do see indeed the van der Waals scaling and the 1/r³ scaling. Okay, and here you can see that you switch from one region to another, but it's another story. You've got another curve which I have not discussed where you can also control the interactions between two atoms using an electric field, but okay, it's not too important. But so it shows that essentially by the end of 2015, the experiments had reached a level of accuracy and precision that allowed you to do that with just two atoms to measure their interaction energy, and then it became possible to envision applications to many-body physics or eventually quantum information processing, although when I look at the number of this morning, which I kind of knew from Patrice, this platform is still far from that. But okay, it doesn't matter. For the many-body physics, there is a lot, and this is what we're going to discuss tomorrow, essentially. So this is all for tonight. So.
Any extra questions for one? Right?
Yeah.
Okay. So the next lecture is on Skype. So, but we will be in the theater as well, because you can interview speakers and ask questions as well, or discuss with speakers. It's not clear. So we will reconvene at 5:50. Try to be on time because the conference will be more efficient organized.
Ok. Donc.
We are in trouble.
Hein?
On est un peu la merde.
Pourquoi?
Très bien. Probablement Covid. Et t'as déjà une question?
Oui.
Sur la slide avec les lasers cooling,
Ouais.
il y a deux directions. Et du coup, la question c'est on refroidit aussi la troisième?
Oui, oui, on refroidit.
D'accord, ok.
C'est juste que sur le dessin,
Sur le dessin, il y a
soit j'ai
pas-
effacé malencontreusement les flèches, c'est possible. Non, non, mais il y a
Ouais,
vraiment...
c'est déjà des choses.
C'est
sur
comme
ça.
ça que ça
Ok,
fonctionne.
d'accord.
sera testé non pas avant mercredi. Donc ça veut dire que toi tu es
I wonder
la semaine
when the reflex phase has a large maximum when it does interact with the electric field,
Yes.
pretty much.
Enfin, tu vois,
Why does it have
si
a
il
long
est testé
lifetime?
positif, c'est-à-dire qu'il est à contact, mais
Because
c'est-à-dire
from my
qu'il va
feeling the stronger it
Le
is,
problème, c'est qu'il n'est pas testé, mais il a tous les symptômes.
Okay, it's a very good question.
Alors,
I will just set up the Zoom stuff because it's a bit critical for the
Okay,
next speakers, and you come back to me. It's an excellent question.
Okay, thank you. Yeah.
Really, yes. And the answer is actually reasonably subtle. So we'll. But okay, I just need to set up the Zoom just in case there is a technical problem.